Hello everyone and welcome to Rebel Way. My name's Andrew Sutherland and today we're going to be creating this air balloon explosion. And this is of course comprised of a few things. We've got some rigid bodies, we've got some vellum, and we've got some pyro. So we're going to go through each one of these. And before we jump into the final project, I thought I'd just do a quick technical overview of the vellum simulation from scratch. So let's jump over to Houdini, and the first thing I want to put down is a grid. So putting down a geometry node, we type grid, and we can see we've got some geometry. But the vellum solver really likes triangular meshes, and here we have quads, and this is going to result in some artifacts. It'll work. You can give it a go. Because essentially what the vellum solver is you can think of it like a particle simulation, and it's going to sim each one of these points as a particle, and it's just going to, collide with our thing. But I'm digressing here. We need to make this triangle, so we can use a remesh node for that. And as you can see, we now have triangles. Let's make our target size even smaller, so we've got quite a lot of detail in our cloth. And from there, what we can do is we can basically put down one of these vellum constraints, and you can think of this like a preset. So we just enable this and we can say cloth. This is now going to set up our settings, and this is a preset basically. And that's all we need to do for a default cloth sim. So, well, when I say all we need to do, we obviously do need to put down a vellum solver. Wire this up. And if we enable this, it's obviously just going to fall. So let's transform our grid up above the ground. Let's say 2 meters. And let's put something to collide with our geometry. So let's put down a test object. And as you can see here, this is our collision geometry. So let's plug this in here. And let's also put down a grid for our floor. So here we've got our grid and our collision. And as you can see, we now have our cloth simulation. Pretty cool. Like I said, we do need to remesh this, because if we don't have that remesh, you'll see. Okay, let's give it some more divisions. In this case, it's not too bad, but you can see when we zoom in, we've got these sort of stepping. And if we triangulate that, obviously, we're going to get a much smoother simulation. Cool. Now, another cool thing that we can do is we can just layer these up. So let's make a copy of this, and let's make this 3. Now, how do we merge this with our sim? So what this actually does is, let's put down a null, and you can see here we've got our geometry, and here we've got our constraints. That's pretty high. So this is our constraints and this is our geometry. So what we can do is we can pack this with a vellum pack. We can copy this. We need this too. We can pack this. And then we can simply just merge our geometry and our constraints together. And then we can unpack and feed this into our simulation. And now we should have both our cloth. Cool. So this packing and unpacking is a great way to just layer up different geometries and constraints. And from there, we can vellum pack this. So this is another use case of this vellum pack. And we can now just save this to disk. Save to disk. So we have this cached disk. And what I want to do is I want to put down this post-process node. Vellum post-process. And we can give this some thickness. But this won't work unless we unpack again. And you can see here, if we give this some thickness, we can make this really thick if we wanted. So you see, we can give this some thickness. I'm not sure why you would want to make it that thick, but you know, something like 0.2. And it just means that we've, you know, this is got a front and a back. Cool. So let's just simplify this a little bit. Let's make a copy. And we don't need the second sim. We don't need this merge. We don't need to pack here. We don't need to unpack here. We don't need this. We don't need this. So the next thing I want to do here is I want to pin some of these points so that they, you know, don't just fall. So what we can do is I suggest making a group. And let's say keep by bounding region. And then let's move this box to select some points. Set this to points. Something like that. And let's call this select points. And then on this vellum cloth node, we can come over to pin animation and say selected points. And let's just see what this gives us. Cool. So you can see now that this is falling as per usual, but those points are now stuck. But what if we say we want to pin those based on some geometry? So let's put down a box. Let's give this some more divisions so we have more points. And then let's put down a group. Let's select points and let's call this group pinned. We can also give this box some animation even. So here I'm going to use a sine function. So sine, it basically puts in a sine wave, and I'm going to call the frame number $f, and this should give us some animation. Cool. And from there we can put down another constraint node. Let's just copy this one. And let's change this preset to attach to geometry. Now, on the selected points, I actually want to just change this side. The reason I'm just doing it on the other side is make sure that it is definitely not this. And let's select just these edge points. So our geometry points are these ones, which we've called selected points. You change this to points, selected points. And on our target geometry, change this to points, and our target isn't showing up yet because we need to plug this into here. and then we can select pinned. Let's multiply this by 4. I see we've got a problem here. We need to make sure that this is not there because we have it here. And now everything is working as expected. I think we're going too low here, so let's just turn this multiplication by 2. And now our cloth is attached to our geometry. Just make sure that you have pinned here, selected points, pinned here, and then on your cloth, remember to remove the selected points that we had originally. So these are our settings. Cool. You can of course pack that, cache that to disk. So from there, let's take a look at tearing our geometry. So what we can do is we can put down a draw curve. Let's change this projection type to this one. Let's template our geo. Let's come to the top view. And let's draw some cuts. Whatever. Something like this. And then what we need is an edge fracture, which is going to give us some detail and fracture this. We can take a look at our exploded view. So we've got some nice pieces. And now if we were to sim this, come back to our perspective, you can see this is just going to all tear and fall apart pretty easily. So let's weld this together. And for that, we can put down a weld node. And as you can see now, our cloth is back together. So all we need to do to get this to break is turn on this breaking threshold. And then just like in an RBD simulation where we set up some rules for breaking apart, here we can break these constraints based on this threshold. So let's see what it looks like at point 1. Everything's falling apart. And then coming to this vellum cloth node, we need to change this to calculate varying and calculating varying. And you can see now that we have tearing in high stress areas. Cool. And this is pretty much all that we need to know to dive into the overall project. So we can take a look at that now. Thanks for watching. See you in the next video. So we're going to jump into the final project that you see now. And the final project was created by one of our students who's done an amazing job. And the only thing I did was work on the explosion. He already had something that worked really well. It was great. We just wanted to add more detail and create some environment fog and have geometry lights that are going to illuminate the scene. So I created those and added them to a scene. But yeah, everything looks great. And we can jump into that project now. Thanks. Bye. Cool. So if we jump into the final project now, and we dive into this render air balloon, we can see here we're prepping our hot air balloon. So pressing A from my keyboard, we can see that this is a geometry that was just brought in from TurboSquid, and this is our geometry. From there, we're converting this to polygons, and we're scaling it to size. Creating a name attribute, and then we're just blasting based on that name. So here we're isolating just the balloon itself, these cylinders, this thing that sits at the top of the air balloon, our metal structure, our leather, ropes, and you get the idea. Basically, this is the wood. We're separating all our pieces. That way we can group these, so each one of these has a group. In this case, we're UV mapping these. So we've got some UVs on here. Same goes for our leather, our ropes, and our basket. Merge that all together, and that's our geometry. Here we've got an object merge, which is just reading in all our stuff. Again, using blast nodes to isolate things. And here we're going to fracture our geometry. So if we take a look at this one, we've got our big metal structures here. And we're isolating this cylinder and all our small pieces. And it's just because this cylinder obviously is, when it's fractured, we want it to be hollow. So if we just add a poly extrude, we can give this some dimensionality. So if we were to fracture this and put down an exploded view, as you can see, with this extrusion, this is now hollow. And without it, this is just going to be big fat chunks. So that's not what we want. And we're just going to save this out to disk. And we're going to do that for all our pieces. And the fracturing is done in here. So basically we've got this little subnet called Voronoi. And we're looping over each one of these pieces. And we're going to scatter points. So here you can see we've just isolated this piece, scattering points on it. And then we can fracture it. And then run over all the pieces. Add an assemble node to create a name attribute. And then out. And if we were to take a look at the exploded view, we can see all our pieces there. Cool. Now this convex decomposition is basically just going to wrap our geometry to make it more optimized. So if we were to take a look at this, for instance, you can see how these pieces are basically just wrapped. So from that to that. And that's going to just make this more optimized for when we send this to the DOP network. From here, we're creating some constraints with a connect adjacent pieces, creating a name attribute. Here we're faceting those points so we can uniqueify them, because what we want to do is we want to scale these lines down to just a point. And for that, we can use a primitive node. And then scaling this down, we scale this down to just 0. And that becomes points. And then we can set a constraint, and this is going to be called hard. And here's like one of those presets that we showed in Vellum. This one is for RBD. And as you can see, this is just a metal preset. From there, we can pack. Same thing like what we did with the vellum, same concept. And we're basically going to do that for all our pieces. So here we're going to do our metal bars. Same thing, treat it as metal. This is going to be glued together. Although, if I remember correctly, we're not actually using these constraints in our simulation. They were added, I guess, with the intention of using them. But actually, when we get to the simulation, it takes fast so quickly that we just have active pieces and inactive. Active meaning that the DOP simulation is going to take over, and inactive means that they're no longer, they're not part of a DOP simulation. They're not affected by gravity. I created a tutorial on an 8080 exploding, and a lot of these RBD techniques are the same. And in this one, even though we do have these constraints set up, I don't believe that they're being used. Basically, they're inactive, and then as soon as the explosion takes place, they become active, and the pieces just fly away. So you don't need to stress about this too much. And we're basically, you know, doing the same process for all our pieces. Treating as metal, packing. Same thing. And since we packed these, we can merge them all together. And then we can use this unpack, just like the vellum. And here we've got this RBD constraint from rules. And what we want to do is we want to create some constraints between our different material types. So these materials all have different groups. You can see that we've got a leather group, a metal group, and a wood group. And here we're creating constraints from metal to wood. And I'm just going to gloss over these because, like I said, they're not really being used. If you do want to take a look more at constraints and, you know, in the use case, to take a look at the 8080 tutorial. And here we're putting down a configure. And here we're setting these points as inactive. I'm going to pack these, and because they're moving, we've got animated ticked on. And as you can see, we've got some animation on here. So this animation is based on a sine wave. So we're basically saying sine, and then this is our frame number multiplied by 4, and then this division, I think, was just done afterwards to dial things in. But basically, this is going to create some sine wave motion, and when you put this on the rotation and the translation, you're going to get some interesting movement. We can see this is sort of swaying back and forth. And a sine wave is, you know, in audio, basically a very pure signal that just moves up and down. It's almost like pushing your speakers back and forth. And if I were to illustrate this quickly, we could put down a sphere. So we put down a sphere, let's put down a transform. And in order to get this to move from left to right, we can just type in $F, and then that's going to use this frame number to move this along this axis. So let's come over to front view. And this is moving quite fast, so what we can do is we can divide this by, say, 10. And now you can see our sphere is just traveling from left to right. So let's try and introduce that sine function. So let's say sine $F. Let's just copy this for now. And let's just make this times 1. Let's see. Okay, we need to increase this. Let's say times by 10. Cool. And let's try. I'm just going to turn my brain off. Let's make a copy of this. Let's make the scale of this one smaller. And then let's trail this. Let's increase our trails something like 50. And as you can see, we're now getting that sine wave pattern. Let's merge this. So now you can see that we've got this sphere and it's moving up and down. And because I'm now offsetting it along this x-axis, you can see that we're getting this up and down sine wave pattern. Very similar to what you would see in a synthesizer. So we're just using this sine function to give some up and down motion along the X, Y, and the Z. And you can see it rotating, you know, it's got an offset here and an offset here, but on the Y, it's oriented up. And this is just going to give it this back and forth swaying motion. So as you can see, we've got some movement on our basket. And like I said, this is all coming from those sine functions. Cool. Here we're unpacking. This seems to be a duplicate, but you can see here we're saving this as animated geometry, and yeah, it makes sense because the animation is coming from here, and so we got it animated, and the pieces are set to inactive. And what we're going to do is we're going to set an active attribute on some collision geometry, and we're going to transfer that that attribute of active onto our basket. We'll take a look at that just now, but for now we've got this set to inactive. And this is a wrangle, I guess, just to make 100% sure that our points are set to inactive. So active attribute set to 0 is inactive, active attribute set to 1 is active. So we look at our geometry spreadsheet, we can see all our points are inactive. Come here, same. So, you know, this is maybe not necessary, but it's a good way to make sure. And here you can see this is where we're transferring that active attribute onto our points. If we look at this now, we can see we've got active as set as 1 on some of our points. And let's take a look at where that's coming from. So here we're promoting the name attribute from the points to the primitives, and then we're attracting the centroid, which is going to give us the point of each piece. We're setting this as inactive, and we're setting a color on these pieces as black. And then here we've got these meta balls. So these are going to be, think of as our collisions. And these switches are just going to turn them on at certain frames. So they're going to pop on as our explosion takes place. And when they pop on, so these are going to pop on, and here you can see we're making a density, and that's just so that we can scatter some points inside. And on this, we're going to set this active attribute, and we're going to set a color to white. So we've got a bunch of black points over here, and we've got white points here. The black you can think of representing as our inactive points, and white as our active points. And if we use an attribute transfer with this condition set here, so we can change this, you know, let's make it back to what it was, 0.1. And what this is going to do is this is going to make some of our points active whenever these meta balls take place. So these are going to pop on when our explosion takes place, and we're going to transfer we're going to make some of these points active. And then, if you notice, if we just take a look at this now, you're going to see that they become active, but then when that meta ball disappears, they go back to being inactive. And that's not what we want. We want to make sure that this active attribute transfers through our simulation. So once it becomes active, it stays active. And for that, we're just going to use a SOP solver, and we're going to read in the previous data, and we're going to transfer it onto here. So basically, this is just going to accumulate So basically, this is just going to accumulate. So we're actually doing the same thing here. We're transferring this attribute, And once this is done inside a solver, it's going to stay active. Well, should. What happened there? Yeah, so as you can see, these pieces are all becoming active and then staying active. And that's done with this SOP solver here. Then what we can do, here we're using this to delete points based on their color. So anything that isn't white or has a value above 0.1. So here we're going to use this color, this wrangle to delete any of the black points. You can see we've got that. So this is just saying if your value is... So here we're just using this wrangle to delete all the black points. And here we're setting that active attribute to 1. So there's a bit of repetition in here, but you know, everything works nicely. You can see how you can just transfer that active attribute on once, and then this way you're using the SOP solver to accumulate that activation. And here we're just deleting all the points, and we're just going to cache this to disk. So when I say delete all the points, we're deleting all the black points, setting all the remaining points to active, and then caching this to disk. And then finally, this is where we're actually transferring that activation onto our points. So if we were to blast all the points that are active, you can see all our active points are now being blasted away. Cool. So from there, we're going to feed this into our RBD simulation. And we've got all the usual suspects. We've got our RBD packed object. We've got a multi-solver. We've got a rigid body solver. And these constraints, like I said, are not being used. Because we're just, you know, if they're active, they're going to take, you know, the explosion is going to take place. We don't really need constraints. They're either attached or not. And so they either need to be active or inactive, and we don't need any constraints. So all we're going to do is we're going to have our collision geometry. This is coming from our balloon, which we'll take a look at. We've got our packed pieces, well, our packed pieces. You can see they're active and animated, so they'll move. We've got our rigid body solver set to bullet. These are our settings. We've got the force coming in from those metaballs. We've got a speed limit to make sure that our pieces don't travel faster than this value. We've got some pop drag to give some air resistance just a little bit, and a pop force to add some noise to our force. So it gives some sort of swirly motion here. That gets all fed into a multi-solver, and we've got a gravity. From there, we want to cache this to disk so we can read in our DOP network and our RBD packed object. That's this node here. And we're going to cache this to disk as points. So you can see this is create points to represent objects. That means that we can just cache the points, it's light, and we can use a transform pieces to transform our high-res geometry. So here we're merging in all our pieces. This transform pieces needs our high-res geometry, our points, and a rest version of our points. So here we just got our points. This is going to be our simulation. As you can see, those points will fly off. So we need to create a rest version of those points on frame 1. So this is just time frozen on there, and then we can transfer this onto our pieces. So as you can see here, we now have our RBD sim. It's looking pretty cool. Like I said, you don't need any constraints. It's just active or inactive. And that is our sim. Here we have some switches and deletes, but it doesn't seem to be working. No need for that. You might as well just disable it or delete it. And a null for out. Here we're deleting everything except for this ring, because we're going to use this to pin to our vellum simulation like we did at the beginning of this tutorial. So as you can see, we're using this geometry like we did that box, and we're creating a group called pinned. And if we take a look at our air balloon, and we've got our leather and our ropes, here we're going to split it. So we've just got the air balloon, just transforming this into place. Remeshing this, so we've got some nice triangles. This should give us, this should mess up our UVs like you see here. So we're just going to transfer the UVs from here back onto our, and that should hopefully make them a bit better before and after. Still not 100%, so maybe try using this labs version. I just don't have labs installed at the moment, so I used this attribute transfer. From here, we're going to use this draw curve to draw some lines so we can cut this up, our edge fracture, and if we were to take an exploded view. So I've just disabled this attribute transfer because it's creating an issue, and I will install this labs version. But if we come over here and we take a look at this now, we've got these draw curves, we've got this edge fracture, and we take a look at the exploded view, we can see our air balloon is being cut up like so. So just round the back, this is our camera. We've got our weld constraint preset, we've got a rest, and we're attaching this to our pinned geo. We've got our cloth constraint preset, set to cloth. And we've got this pressure constraint, which is going to try and keep this shape as much as possible. As you can see, we've got a whole bunch of constraints here. Let's put a null. Yeah, so I've just reducing the amount of points here so we can take a look at this pressure constraint. As you can see, there's quite a lot of constraints, and that's going to maintain this shape. And from there, we can feed this into our vellum solver. And here you can see our gravity is set to 0 on these frames. And then after our explosion takes place, you can see this is set to -7, so the gravity will take over at this point. So our settings, and our unpack, and then we're going to just save this to disk. So as you can see, this is a bit distorted, so what we can do is unpack this and put a vellum post process. And we can put some smoothing. So here we're smoothing out these details a bit with this vellum post process. And this is our main balloon simulation. From here, of course, we want to group these points. So here we want to attach these ropes to our ring here. So we're just selecting these points here. Deleting everything. I think this guy should not be selected. It's fine. Let's see. Yeah. So you can see that we attaching this to here, 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 and here, where all these little lines are. Our constraint type is string here, so it's our preset. And we're feeding this into the solver, unpacking, and saving out to disk. Come up here. We've got our leather. This is still our string. You'll be creating UVs on each one. Like so. And then, like I showed before, with those ropes cached. Now they just got UVs on them. Coming up to this one, this should be our leather. Remeshing. Transferring the UVs back on here. And the same process that we showed before. We're selecting these points. As you can see, this is where this is going to stretch to. And caching this to disk. Merge those all together. For these UVs for now. That is our vellum simulation for our ropes, leather, and balloon. Here, of course, is all our metal structures. And we're going to merge those together. And that is our final balloon. And all these techniques are the techniques that we've gone over in the beginning of this tutorial. So if I went over this a bit quickly, go back to that first part. Everything is there, and you can just take a look at how that technique was implemented in this scene. Saving this out to disk. Yeah, I need to fix these UVs still. I will do that. But basically all I will do is install labs and use that attribute transfer. Here I've just got my material and I'm using Arnold, and I'll set up some color on our balloon. Cool, that's it for the RBD and the vellum. All we need to take a look at next is our explosion. So we're going to take a look at the Pyro simulations now. So this is all our Pyro stuff, and we're using this Pyro burst. So if we take a look at this, you can see that we're starting this on frame 46. And essentially what this is a bunch of points, some noise attributes on it, and we're going to use this for our initial source geometry. So if we take a look here, we can see the shape. This is just an offset, or yeah, this is going to give us some variation. The initial size, the spread angle. So this is pointing up. You can play with all these settings. The number of spikes. The variation which is linked to our trail length. So our variation is always going to be half whatever our trail length is. This is our thickness here, and I just use this variation to thicken things up. This is only going to take place for 5 frames. And our points have density. We've got this noise. Without it, it's just uniform, although it does fade off towards the ends. So there's higher density here than there is up top here. And if we enable this noise, that's going to multiply this noise and give us some more breakups. And here we can add some velocity. Cool. So those are the settings for our Pyro burst. Then we put down a Pyro source. And this is just going to take our points and create a density attribute. We're going to transform this into place, just so that it intersects with our geometry. That. And we're just going to layer up a few of these. So here, this one is, got even more spikes, which will take place on frame 48. So it's just 2 frames after our first one. And this one has some noise on it. So this is going to be our first initial spiky one. And then this is going to be our big one. From there, we're going to rasterize these attributes. So creating a density, so this is now volumes and V, because this is what we need for the Pyro solver. And an extra VOP to add some more noise. So here we just adding this AA noise and another version, adding these to our density. So it's going to give us even more breakup. Here we're just clamping our values, so our density stays between 0 and 1. This just means that we can control, I like clamping things or normalizing. So having values between 0 and 1 just means that it's, when you do multiplication down the line, this is going to be easier for us to work with. And we're caching these out to disk. So first one and second one. So this is our source, and this one we're going to rename as pump. So we can have this is going to be bring in our data, and this is going to manipulate our data. So we're going to use this to like inject more velocity into the simulation. And sometimes we like to expand this. So as you can see, on this one, our particle scale is 0.4. And on this one, it's 1. And that just means that basically our source is inside of this one, because we want this pump force to affect, to encompass our source geometry. And same thing for our second source. And from there, we're going to feed it into our DOP network. And the bare minimum that you need for a smoke solver is a smoke object, our Pyro solver, our source geometry, and that's it, really. That's the bare minimum. But of course, we want to add some detail to this. So we've got some disturbance, another disturbance. This is disturbance based on the speed, and this is disturbance based on gradient mask, and some gas vortex confinement, which is just going to exaggerate the details that we've already got, and some turbulence. So turbulence I often like to think of as my broader strokes, and the disturbance is like the fine detail. So turbulence I like to use to sort of break up the overall shape of my explosion, and disturbance is adding the fine micro detail to the sim. Of course, you can also use turbulence to add surface detail, but I tend to think of turbulence as breaking the simulation within, and disturbance is adding detail on top. And what we're doing here is we're sourcing our density and we're pumping that into divergence. And what divergence is the expansion of our simulation. So as you see a gasoline explosion, it sort of expands outward, and that expansion of gas is divergence. The density goes into density, creating smoke, and our velocity goes into the vel, and that's going to push our smoke in the direction of the velocity. And then of course we're using this pump, and you can see the the pump is going to this pump force, and you can come over to this initialize and tick on pump. But essentially this is going to set this up as pump into pump and V into vel. And what this will do is this is going to give our sim more impact, and it's also going to try and retain the shape of our simulation. That's why we expanded our VDBs to encompass the source, because we want to keep that spiky shape of our simulation, and that's where the pump comes in. The pump can be quite useful in maintaining the shape, because if you push a lot of velocity into a simulation, you'll find that you get these mushrooms at the ends, and that's kind of what I like to avoid. Is we want mushrooms, like explosions do have mushrooms, but you don't want them at the end of all these spikes. So I try and get the expansion to be in the middle, and then use the pump force to sort of pull our smoke in the direction of that pump. That's the way I think about it, at least. And then same thing for our next source, same thing for the pump. These are just our values, and you can see this divergence is animated here. So it expands at first and then goes down. And when you expand the divergence, a lot of the time what happens is that you lose detail, because if you think about it, you're creating detail, but the volume is expanding, so that detail gets lost. So when I animate divergence, or I use divergence, I also like to animate my detail. So the stronger your divergence, the stronger your disturbance should be, and then as that trails down, I trail down my disturbance value. So we'll take a look at that here. So if you can see, okay, this one is not animated, neither is this one, and this one is. So as the divergence starts, you can see we've got a very high value of 5,000, and as the divergence stops, still 5,000, but here it should trail down to 0. I don't always trail down to 0. You know, sometimes I increase it a bit. You know, it depends on your simulation. You just kind of have to balance these values a bit. The block size is the size of the detail, and it's usually, these are the things that I'm playing with. I'm playing with the strength, and I'm playing with the size of the detail. And these are controlled by this control force, this mask called gradient mask. Basically, what we're doing is we're creating a custom field called gradient mask. It's like a copy of the density, but we're going to manipulate it. Here we're creating gradient and gradient mask and gradient. This is based on the velocity, and this is based on the density. This is just what we need to do to analyze it. And the gradient, you can think of it like the normals of a volume. So it's like the very outside part of our simulation. And we also need to advect this. So we need to get this to accumulate through our simulation, we need to use this gas advect. So this is what this is doing. And these are our settings, BFC and set to clamped, same as our simulation here. This is BFC C and clamped. And let's take a look at how this mask is actually being created. So we've got this gradient. We've got that being analyzed here. So that's based on the velocity, and this one's based on the density. So what we're doing is we're computing the gradient, we're normalizing that, so we're making sure that the values are between 0 and 1. Same with our velocity, and we're computing the dot product of these two. And what that means is, So think about the gradient is the outside surface and the velocity is the direction in which it's traveling. And where these two are aligned, we're going to keep that mask. That's going to be known as our gradient mask. So here's the surface and it's traveling in this direction. So here is where our gradient mask is, and then it's going to fall off along the sides. And I'll create a visualizer just now so we can take a look at this. And then it's being fitted into this ramp so that we can mask it, and we're exporting this as gradient mask. And what's cool about this is that we can then add detail to this gradient mask, and our details are only going to show up on the surface and at the very leading edge of our velocity. And that way we can be quite aggressive with our disturbances, and it's going to only disturb that part, and what's being left behind is untouched by our disturbance. And that creates this very natural, very cool looking explosion detail. So this is my favorite mask to use when creating explosions. I hope that makes sense. I will either make a bit more of an explainer in the here, or we'll visualize this mask so we can take a look at it. But that mask is basically being used on our disturbances here. So this gradient mask, this one with this very aggressive setting, and what I like about this too is that it also seems to maintain the overall shape of our simulation. So you can try and dial in your shape as best as possible at your source, and know that you can then just add detail to it with this gradient mask, and then you can break up your overall shape with the turbulences. Let's take a look at these fields. So let's take a look at these custom masks. I have a feeling that this, because I don't see this field is here. So we've got divergence, gradient, grade mass, and speed, and this disturbance is masked by speed, and this gradient is masked by our gradient mask, and this disturbance, I should say, is masked by our gradient mask. But I think that this speed is everywhere. It seems to be adding detail everywhere. Whereas this one is our mask that I like, this gradient mask. So let's jump to the stop imports and let's import those fields. So here we can import that gradient mask, and we can set this to smoke, that's fine. And this one we can set as speed, and let's set this to invisible. Cool. And what we can do now is put down a volume visualization, and let's take a look at that gradient mask. Come over here and we set this to infrared. Now we can see our mask. So the red parts is going to be where we're adding a lot of our disturbance. Our green not so much, and our blue none. So let's just let this run through. In fact, let's lower our settings quickly and let's just run a quick sim. Let's multiply this by Okay, cool. So we can take a look at this gradient mask now. And like I said, this is basically the coolest mask ever, because what you can see here, the red is where we're going to add our strong values of our disturbance, and then it's going to fade off through the green, and on the blue have no disturbance. And what that means is that these leading edge parts of the explosion is where we're going to put our detail, and the blue parts is going to remain untouched. And this is going to give us, we can be aggressive with our disturbance, so we're going to add lots of detail there, and then the blue is going to remain untouched, and the overall shape of our explosion should hopefully remain intact, but we're just going to add detail where we need it. So this is my favorite mask for explosions, and it's a very, very powerful technique. Let's take a look at the speed, but as I suspect, I don't think we've got, I think it's everywhere. So let's just take a look. Okay, no, so we do have some mask, but for the most part, it is everywhere. And I think our range was between 1 and 2. Okay. Okay, so now we're going to take a look at our speed mask. And as you can see here, it is slowing down now. So as our explosion is fast, we're going to add disturbance, and then it's going to fade away. Although it is going quite fast here too. Interesting. This mask looks more like an age to me. Anyways, we're adding detail in the first few frames, and then it's disappearing. Cool, so those are our masks. And if we come over here and we can take a look, these are our control fields, and this is my main control. Also the gradient mask. This is just going to exaggerate, like I said, and our disturbances. This is just breaking up our temperature. Same. Cool. So that's it for our pyro simulation. Our buoyancy is animated. So as our explosion first takes place, so our buoyancy goes from 0.5 to 0.2. So we don't have much buoyancy. Our explosion isn't traveling up very much. And our expansion rate, which is like our divergence, that is animated here. So here's high divergence, and then it's brought down by frame 77. On our settings, here you can see this is where our expansion is animated. Our shape, just a bit of dissipation, since all our disturbances and turbulences is all being taken place with our microsolvers. Sparsity, this is off, and our advection type is BFCC and clamped. And you just need to make sure that if we've got any fields here, that these need to be changed to BFC and clamped too. From there, we're just going to import those fields, and we don't need the speed and the gradient. I was just using that to show you those masks, and we're just importing the density, velocity, and temperature. And we don't visualize the velocity. We only look at the temperature and density. So if we put down this Pyro process node and we say resample the velocity, we can lower the resolution of the velocity, since we just wanted, maybe we want to advect the cloth, maybe we want to advect another Pyro simulation. So we want some velocity, and we want some velocity for our motion blur, but we don't necessarily need it to be high res. So we can just resample that. We can convert to VDBs. I like to render with Arnold. Arnold likes VDBs, and we convert to 16-bit float. And this is just going to save us some disk space, and then we save out to disk. From there, we can put down a Pyro bake, and this is going to determine the look of our explosion. So I tend to just use the density and the scatter, blur it, and enable masking. In this case we are using the fire, but it's not really adding too much. In fact, I might do the render with this off, and that's about it. From here, putting down attribute delete, and I'm deleting everything I don't need. Oh, something very important I forgot to mention. Because I like to render in Arnold, I come over here and I tick on bake emission volume as CE. And this means that I can use this Pyro bake look, but without using mantra or comma. I'm going to read this CE attribute into my shader, and that's how I'm going to create the look in Arnold. So if I come over to this shader, here's my Arnold shader. And as you can see, it's very simple. I'm just importing that CE attribute. I'm computing the length of that. And then I'm just feeding that into the emission. And the CE is going into the color. And then I'm exporting that as volume. So, and under the shader here, I've changed this emission to channel. So that's going to read that CE. And I've set my density to 15. And you can play with the colors. But that is basically my Arnold shader based on this Pyro bake workflow. So that way I can just use Arnold. And it's slightly different. So if we take a look at this here. Okay, in this case, it's quite different. But you can just dial this in and get it to be as similar as possible. It is possible. But this is my preferred workflow. I'm just trailing this again, computing the velocity. We don't need this trail, and I don't think we need this post process because we already did that up here. So I can just delete this. And we're deleting everything except for the CE and the density, and I'm just adding the motion blur in comp and nuke. So that is my sim. Cool, and it's the same process for all the other explosions, just some other minor tweaks. So if we take a look at this other explosion, it's the exact same process. Here I just have 2 caches and I have the switch because this scene was created by one of our students, like I said. And what I was doing is I wanted to add some details to his explosion. So I was running a sim, caching it, taking a look, changing my settings, and then caching it to this node, and then I was just switching between the two so I could compare my simulations, and so I could take a look and pick the one that I liked the most and then stuck with those settings. So that was just my process there. Can't remember which one I ended up going with in the end of these two, between these two, but they're both working. And then here we're blasting everything but the velocity. We're resampling this like we do in that Pyro post-process node, and I'm just saving this to disk and putting this as outval. And because we've got this last one, which is slightly different in that we've got this node here and we're reading this explosion vel, and this is just going to advect this explosion with the previous one. So there's going to be the velocity influence from our previous explosions on this one. But yeah, everything else is the same. We've gone over this. Cool. And that's it for all our explosions. Merging them together here just for visualization. And that's it. So that's it for our explosions. Just reading these in here. Trying to optimize. I don't think I need this trail. Wasn't rendering with motion blur. Just deleting all the fields I don't need. I don't know why I'm post-processing this so much. Again, this has already been done. Deleting everything that I don't need. So this is optimized as possible. Saving out to disk. And then I've got my material, which is that CE shader. Cool. One other thing that I wanted to do is I wanted to create an environment fog. So for that, I just made a box that encompasses our scene, created a VDB from that, converted to VDB, 16-bit float, save this to disk, And then I just put a material called volume fog. And this is just a simple Arnold shader with a very low density, something like 0.1. That's it. And the other thing is I wanted to create a geometry light based on my explosion. So what I'm doing is I'm reading in my explosions here, merging them all together. For the millionth time, I seem to have added a post-process node. I need to get out of the habit of adding this to everything. Blasting everything that isn't the density. VDB reshaping this, so just to blur it out. Converting this to an SDF. So now we have this as a surface, and you can see I'm moving this ISO offset. So you can shrink it in or expand it. That was my settings, and from there I'm converting this into a mesh, and once again I'm eating this in, something like that, right? From there I'm just reshaping this. It's not really doing anything actually. And here I'm transferring the color. No, I'm transferring that CE attribute. So as you can see now, I've got, I've just got the color, name, and whatnot. And now I want to transfer that CE attribute. And then if I put a color on here and I map it, you can see I've got the color from our explosion on here. I'm smoothing that. Well, smoothing the geometry. And I'm smoothing the color. I think this is just a multiplier, so I'm just adding some color here. Yeah, make it a bit darker. Actually, it's a bit lighter. Smoothing the color. And saving this as a geometry light. That way I can put down a Arnold light here. I can set this to mesh, and I can just drag and drop this geometry light over here, and these are my settings. And what this is going to do, this is going to illuminate our fog, and it's going to illuminate our objects, and it's a very cool workflow. The other thing I've done is I've come over to shader here, and if I dive inside, I can decay this light. So if I were to come over to my render view and take a look at my volume fog, let's take a look at our, and we need to come over to frame where something takes place. On this render here, you can see this light falling off, and that is coming from this decay. If we make this smaller, you can see it's more isolated to just our explosion, and with the value of 15, it's more spread out. And under my AOVs for this, you can see I've got my mesh light, and I've got my environment light, so you can play with those in comp. And that is just set up here. So we're forcing the environment, we're excluding our, this is where our simulations are made. And then for our phantom is our geometry light, and we've got these sparks, which I'm not really using at the moment. And then we force matting our explosion and the vellum and RBD simulation. And that's it pretty much. The explosions rendering, we've got some multi-scatter, and we've got direct, indirect, volume, emission, environment, light. And if we want to set up AOVs for the light, you just come over here and use type in ENV for environment light, and this one is mesh. And then on our Arnold node, you just type RGBA and then that whatever that name is that you typed. So I'm just briefly going to go and take a look at these sparks. And we have a Pyro burst node that we've already gone over. This starts on frame 57. So here we can see this is our Pyro burst node. These are our settings. And this is set to points. We're transforming this into place. We're transforming this, adding some noise to the position, adding another noise, deleting all our attributes except for P and V, reducing the number of points with this slider. Here we're deleting these white points plus a random amount. So without this, you can see it's just these points down here. And with this, we're just going to remove some randomly. You could have just used a clip and then increased that slider to get the same thing. But this works too. Another way of doing it. And then we're just removing that group because we exported this as a group called remove, group remove. And from here, we can read in that our velocity from our explosion. And then we can pass this over to a particle simulation. We're birthing particles as long as the frame range is below 61. You can see after 61, this value will change to 0. Whereas before 61, it's a value of 1. So we're streaming in that data. We've got a life expectancy of 3. And this is set to all points, first context geometry. And then we're going to advect that from that second input, which is our velocity from our explosion. And then this is just going to remove any particles that aren't moving. Cool. And an out. Then we can cache this to disk. Here we can set a particle scale, which has got a bit of a randomization between 0.2 and 0.5, and a normal based on the velocity. And then we can copy lines to our particles. From there, we're just going to noise up this a bit. And then we've got a resample. We're just using this to compute the curve view. So this is going to give us a value from 0 to 1 based on the first point and the second point. So the first point is 0 and the second point is 1. And then we're going to get a nice gradient along. Well, although I'm not seeing that here. I think this is just random. So yeah, we're taking the ID, we're fitting that into random, and we're feeding it into a ramp, and then exporting as color. So this is just going to assign a random color to these. And then I think here we're using this curve view. We're using the curve view to set some transparency on the beginning and the end. So you can see that like that. Cool. And that's it for our sparks. Cool. So that is it for our sparks and all our simulations. Please like, comment, and subscribe. It helps with the algorithms. And I'll see you guys in the next tutorial. Thanks for watching. Bye.